basis. Number 3 is computing the area of this one, and then figure out a vector that is perpendicular to this vector E1 and E2. So the area is not absolute value of E1, norm of E1 times norm of E2, because this is not perpendicular. So you have to find one that is perpendicular. So here's the one way. I'm projecting E2 onto E1, right? Projecting E2 onto E1, and that's this some vector. It looks like perpendicular, but with respect to that inner product matrix, it is not. So if you do the projection, that projection is this guy here. Project E2 projection onto E1. It is E1 times the scalar. That was just what we just talked about. So if you subtract it off from E2, then that's going to be the perpendicular component. This is the projection of E2 onto E1. And if you subtract it off, it's the other perpendicular part. So W will serve as the height of this parallelogram. So the length of a W is be multiplied. The length of a W with respect to our inner product metric is this one. So you multiply this one to the length of a base. So that's the height right here. So E1 is root 2. And W I just calculated using the inner product, and it turns out it's root 3. Does that make sense? Yeah. So that's that. And what about V? How are we going to find the V? V is supposed to be a perpendicular to the given E1 and E2. Something is sticking out like this, so 3-dimensional, but it's not the usual perpendicularity. So you put this condition V E1 and V E2 all 0. That if you pursue, this is supposed to be ABC here, since I'm using ABC, but that's the typo. So you solve this equation. It turns out it's 1, 1, negative 3 is one of the things. And you understand that once you have a vector, is all scalar multiple is still perpendicular to whatever this one, just like in that. So you have to play with the scalar to find the right area. So what is the length of this vector? Is that you've calculated T's there. I forgot to put squared. I did squared. Okay. So what is the length of this one squared? Turns out is 3. Okay. So T times that is, turns out the formula is 3T squared. We want to match that to area squared. So what was the area? Was 3 over 2 there, right? Just a 3, so it's a 3, so T must be plus minus 1. Therefore, you can choose plus 1, that's one direction perpendicular. The other direction perpendicular is the magnitude doesn't change. So that's one way to find it. So it's not bad. Finding one example like this is not bad. The challenging part is that, wow, how are we going to do this thing in general? And that was the challenging part. And it's very difficult to carry that idea to over in here. So this was really the challenge. The idea is the following. Remember, actually, we're looking at these matrix and the coordinates there with respect to the standard vector E1, 1, 0, 0, 0, 1, 0, and there's a metric. But you can imagine that actually came from usual dot product. There's a W1, W2, W3 sitting inside R3 with a usual dot product, such that if you dot it to itself, it becomes 2. Dot it to itself becomes 2. Dot it to itself becomes 1. If you dotted each other, it becomes all 1. So how this one behaves under the dot product is exactly how that E1, E2, E3 behaves under this matrix. Because if you all that we're going to use is the value of inner product, then this guy has same inner product value. So the geometry is exactly the same. So in the loose sentences, I wrote it here like this. Geometry induced by the inner product on this R3 that given by the matrix is the same as this one with a dot product, treating as if this is E1 and E3. So here I'm giving a more mathematically specific statement in here. V1 and V2 is this A1, A2, ABC in here through that matrix new inner product, which is this one in here. That's exactly the definition of inner product, this one. And I'm claiming that, all right, let's look at this A1, W1, B1, W2, C1, W3 dotted with A2, B2, C3 through the dot. This is not inner product, usual dot product. So this u1 and u2, see how that behaves. If you really multiply that out, I'm doing this like this. This is another neater way to kind of using the compact notation. Remember, this is scalar, and w1, w2, w3, and these are column vectors. And that's exactly what this one. This one, a1 multiplied a2 multiplied b1 multiplied c1 multiplied in there. So that can be compactly written as a matrix multiplication form. It's a dot product of that, right? But the this whole thing is a column vector. One column vector dot product of another column vector is the same as transpose. Show it like this. If I have one column vector ABC, dot product another column vector A prime, B prime, C prime, of course you multiply these three things, right? But as a matrix multiplication is the same as ABC, ABC here. We've done this multiplication a lot when you calculate inner product, so it's the same thing. So I'm doing it here. That one as a column vector transposed. And then matrix multiplication is what it is. So if you transpose it, they swap the order. You actually transpose it. And if the column vector transposes the row vector, and then they're isolated like this. Whatever this one and you're seeing inside here better be this one, because it's trapped it in there. See, this one is multiplied to W1. That's a 1, 1 column. It's really neat to see this. W2 multiplied to that one is a 1, 2 entry, and they're really dot product. So you can see this matrix, 3 by 3 matrix, is consistent of a dot product of these individual column vectors, and the index is a perfect matching to that. So that one we obtained it exactly to be like this. So they agree the inner product of this one is a dot product of these two things. So area formed by these two things is the area formed by these two things is exactly the same thing. So that's the key behind. Then still is some calculation, but it's a lot better than approaching in general. So here I'm saying the area of a parallelogram formed by V1, V2 with respect to that inner product is just a parallelogram formed by U1, U2. In our Calc 3, use a dot product, and you can calculate that. And V3 being orthogonal to V1 and V2 with respect to that inner product is the same as this thing, whatever that is, orthogonal to W and W2 through the dot product. So I'm using the word perpendicular instead of orthogonal. So let's find that WKs and use this idea to actually calculate. So what is WK? Is first I started with the W1 being 2, dot product being 2. That 2 came from the first entry in here. So easiest one, I don't want to use any square roots or anything. It turns out 1, 1, 0 is easy. So you actually have to do this dot product. Just dot product. This is not inner product. It's a dot product. It's really easy. It's 1, 1, and 0. 1, 1 plus 2. And then dot product 1 and to itself 2. That's what we read from the matrix. So a plus b equals, a squared plus dotted to itself 2. And it seems like a simplest one using some 0 seems like this one. So this 2 is a perpendicular, not perpendicular if it satisfies this condition. Third one is that it has to be dot product of 1, 1 here to itself is 1, and that's the lower right corner element. So you looked at it here, try to make it as simple as possible, and there was 1, 0, 0. So it's pretty simple. If you look at these three vectors, their dot products matches exactly this product matrix there. So the next part goes like this. The cross product of these two vectors, u1 and u2, which is w1 and u1 and u2, which correspond to a1, b1, c1, a2, b2, c2 with the inner product, right? So that's that. If you're the cross product, if you do that through the dot product, the Calc 3 method, that cross product will be perpendicular to that and perpendicular to that with respect to dot product. But that's the same as column vector a1, b1, c1, a2, b2, c2, and is orthogonal through that vector. So that's the idea. So I think I'm calculating this u1 and u2 using the usual, what is it, cross product formula. And I got this answer, and right here, that's the answer. But this answer is always written in, wait a second, am I doing this right? Right, I'm actually multiplying out. I put it into usual column vector form, put that into usual column vector form, so that I can use the cross product formula. So I did that, and this coefficient are usual column vector, so it's be written like this, and vertically actually written like this, not that one. I think so. Yeah, it's this one. So we don't want this vector form like this. We want this vector form in the form of A3W1, B3W2, C3W3, so that we can interpret that coefficient into the inner product world. That's another challenging part. Once you do the cross product, what you get is the expression with respect to the standard base. But you want this one with respect to actually the W1, W2 base, so that you can interpret this coefficient correctly for the inner product world. So I have these coordinates, and what is this A3, B3, C3? And again, it's an equation. You have to put it into a matrix multiplication form. Then one A3, B3, C3, and there is this vector in here, so that P is known. We have calculated all this. So what is this one? You simply multiply inverse matrix, right? Matrix inverse there, and that's the calculation. Inverse was nice, like this. There's no division or anything. So I multiplied it inverse, and I got these three different coordinates. X2 here is some of the thing that is involved in here complicated, so I substituted. So x1 is the sum of AB1, ABC in the first vector. x2 is the sum of ABC in the second vector. So they go all there, and everything is in terms of A and B and C. All right. So that I claim that is the vector. That is a perpendicular with respect to that inner product, and this area of the magnitude of this vector is the area of the bottom parallelogram, all in terms of with inner product. That is the nice property of the cross product in the three-dimensional space, right? So of course you want to verify this is really true. So I'm doing this one. Area, this is a formula, I have it here, right? So this W is a perpendicular part, orthogonal projection part. Just like that part A, I did it. So this is orthogonal projection. And then all of this thing I can calculate with the V1 and V2 is A1, B1, C1, A2, B2, C2 through the inner product matrix. All that I calculated easily in here. And then I multiply these two, and that must be the area. Bottom and the height. And V3 I calculated here. Its magnitude square must be the area squared. So these two things. So I did that calculation in Mathematica. I think I have it here. I hope it's not too small. So that's the matrix, and that's the inner product I defined in Mathematica, and this is the formula of a V3. I put in everything in there, just like in the formula. So I got this formula in V1 and V2. I'm doing this formula, the orthogonal projection, and the W, so I'm multiplying W, inner product W, that's the norm squared. And this is V1 and V1 norm squared, so that is supposed to be the area here. So that I'm calculating through the geometry. So I'm comparing these two, W with V3 I calculated here, norm of V3, and they're calculated here, and simplified it. It was the same thing. All right. So that was one tough problem, unless you see this connection. Even if you see this connection, most challenging part could be entering this one, reinterpreting this one into correct coordinate system for that. Once you have that, rest of the part is kind of not that deep, but in that multiple challenges. All right. Suppose we don't have this interpretation, and what is there any other way to do it? Here I'm explaining exactly the way the cross product is explained. But usual textbook does not use this much of a matrix algebra. But using this matrix algebra and Cramer's rule, I realized that half of the students in linear algebra don't know about the Cramer's rule. But using the Cramer's rule, which is a solving matrix equation, straightforward. There's no row reduction, nothing. There is just closed formula using the determinant only. So using that, you can kind of read through this different formulation. So my solution in an earlier case depends on my discovery of W1 and W2, W3, right? In general, that could be quite tricky, right? So this one does not involve that. So it mainly uses Cramer's rule. So final answer look like this. A is that matrix. A1 is missing first column. So it's a 3 by 2 matrix. A2 is that matrix, inner product matrix, missing the second column and third column. If you multiply this to odd size of the matrix, it becomes 2 by 2. 2 by 3 times 3 by 2. So it becomes 2 by 2, 2 by 2, 2 by 2. If you calculate these determinant of 2 by 2 matrices like that, and that becomes x and y and 0 coordinates of a cross product with respect to that inner product. All right? So when you do the cross product, you know there's this alternating sign convention kicks in there. So I did it here, down here. So that's first column missing. Do you see that? Second column missing and third column missing. So I created this common matrix that is keep multiplied to A1 and A2, A3. And I actually did it here. Multiplied and multiplied and multiplied and determinant. And I got one version I call V33, and I calculated V3 here, I calculated over here, right? So I took the difference. They are the same vectors, so the same formula. And this one does not involve clever choices of W, W, and W2, 3. And to understand this solution, you have to understand Cramer's rule fairly well, and my clever setup of this XYZ. And also is explained in the very first, it's in my Calc 3 YouTube video. I explained this first setup in here, this 3 lines right here, detail, so that you understand the cross product formula you learn in Calc 3 like this. That's why that formula looks like this, and that's explained in here. So you can see we just entered something called orthogonal projection. Isn't that what we did last time? Orthogonal projection. That's all. I give you 2 vectors, and I have something else over there. And what is the orthogonal projection? You want that perpendicular vector. So this is exactly the business we're talking about. And you can even generalize this one in here. Do you easily see how to generalize this one? If you were in the 4-dimensional space, it's going to be 4 entries and 4 entries and 4 entries. Yeah, but think about it. If it is a 4-dimensional space, you need 3 vectors to enforce 1 remaining vector. Does that make sense? Yeah. If it's 3-dimensional, you need 2 dimensions to force the perpendicular to be in 1-dimensional world. Like that. So if it is a 4 entries, you're going to have 3 rows. And then you're going to have a 4 by 4 missing 1 entries there, right? And so on. So this formula will still work. That would be a wonderful formula. If I have 5 vectors in a 6-dimensional world, I want that perpendicular vector to the orthogonal projection, right? And there is a procedure that I introduced in today's homework. However, this one is like a closed formula. It's like a master formula. If I have, Mathematica and then put it in there, and then it's going to do it in a 1-line formula in here. And if it is a massive formula, it wins over row reductions and a lot of things. If you think about it, amount of computation goes through, often this guy wins. But we don't usually have this thing. So the algorithmic procedure is usually the first thing we approach. But there's this wonderful formula. I hope this generalization of this one to n-dimensional space is clear. I'm going to make it just a lecture review exercise. So Make sure this one, does that make sense? There's n minus 1 rows here, and n by n matrix missing one column. They're all multiplied. And then there got to be, this is tricky. You never did this many alternating thing in Calc 3, but it's got to keep alternating, remember? Plus, negative, plus, negative. Then you have that vector that is orthogonal. It's a wonderful formula for that perpendicularity. You don't